Converting differential equations to algebraic equations is a good idea because it makes life simple. One such method, the world's simplest method, is the finite difference method. So here we will replace the derivatives with finite differences, do some number crunching with it, and also we'll talk about the limitations of the method. Okay, so first we're going to see how to replace the spatial derivative, then we'll see how to replace the time derivative with finite differences. So here is the problem we're trying to solve. This is a slab, and we're going to do heat transfer in a slab that is being heated symmetrically. So initially it's at this temperature, and it starts to be heated with the temperature on the surface being changed to this. And so the two boundary conditions are the surface temperature is given and it is symmetric. So the condition here is del T del X at x equal to 0 is 0. So those are the two boundary conditions. With that, we're going to solve the heat equation, and or we need to solve the heat equation. That we're not going to solve the way that we know from our differential equations class. Instead, we're going to replace this equation with an algebraic equation. So as you can see, this is a straight algebraic equation with additions and subtractions. So it's very easy to solve. So we're going to go from here to here, and that's what the process is about. And you'll see that we do this but using our most basic understanding of a derivative. So let's do this. First, let's do some basic maths going back to the first days of calculus. Here is a function f of x that is continuous, but we will discretize it, talking only about discrete location. So for the position corresponding to x, we denote it as I, and for the position corresponding to x plus delta x, we will denote as I plus 1. And for the position corresponding to x minus delta x, we'll denote it as I minus 1. And the half points between I and I plus 1 would be this I plus half, and point between I minus 1 and I is this I minus half. Using Taylor series, we can write f of I plus 1, f at I plus 1 is equal to fi plus delta x over 1 factorial del f del x at I plus del x square over factorial 2 del square f del x square at I, and so on. Okay, and now we want to solve for the derivative because that's what we are after. So if I write del f del x on the left hand side, that's equal to fi plus 1 minus fi over delta x minus del x over factorial 2 del square f del x square at I, and so on. Okay, now if I approximate the derivative keeping only these first two terms, then we are in effect dropping all of these terms, and the one that is the highest in magnitude would be this first one, which is of the order of delta x. So we say that this approximation of derivative is of the order of delta x raised to the power 1, which means it's first order accurate. And we'll see that there are other ways of doing derivatives. We can do this differently using Taylor series at I plus half, writing it in terms of I. We can write f at I plus half is equal to fi plus delta x over 2 over 1 factorial del f del x at I plus delta x over 2 squared over 2 factorial del square f del x square at I plus del x over 2 cube over 3 factorial del cube f del x cube at I plus higher order terms. And likewise, we can write the value at I minus half in terms of the value of I as f at I minus half is equal to fi plus, let me just write this way, minus delta x over 2 del f del x at I plus minus delta x over 2 square and del square f del x square at I plus minus delta x over 2 cube over 3 factorial del cube f del x cube and so on. Okay. Now again we are after solving for this del f del x. So if we subtract the second one from the first one, we get f at I plus half minus f at I minus half is equal to delta x, that's these two of this one and this one together, delta x times del f del x at I. Then the next one, these two, this guy and this guy, they cancel out because this is squared, and so it's the same value. And then the next one, they add up, so I write 2 times delta x over 2 cube over factorial 3 del cube f over del x cube minus and so on. Okay. So now we solve for del f del x at I is equal to fi plus half minus fi minus half over delta x and minus 2 times delta x over 2 cube over 3 factorial del cube f del x cube And because we divided by delta x, this will become square, and minus more of these higher order terms. Now, if I define the derivative by this formula, which means effectively I am dropping all of these higher order terms, then the largest one of these terms is of the order of delta x squared, as you can see. Okay, so we call this formula as second order accurate, whereas the one before was first order accurate. So because delta x square would be smaller than delta x for small delta x, then we say the one that is with the square, it's second order accurate. So in other words, it's more accurate. Okay, so this formula for getting the derivative is more accurate than the other one, and notice this one goes half a step ahead and then half a step behind, so it's called central differencing. And so central differencing is second order accurate, and it is generally a better approximation that we want to use. Back to the heat equation. We will apply the formulas that we just derived to the heat equation. That's this one back again. And first, we're going to apply it to the spatial term. So I want to write a finite difference form for this term at I. So here, which is the location x. Okay, so at location x or I, and that I can write the second derivative as the derivative of this term here at the same location. So this quantity inside the bracket is like my function f that we had been talking about. So this is like f of x. And so we can write this using central difference. So these 2 points, so the value here in terms of the values as at these 2 points is equal to del t del x at I plus half minus del t del x at I minus half over delta x, right? That's the central difference, and it's second order accurate. That's what we saw before, and now we repeat the process. So now this time the function would be the t. So I write the first one, this one. So we're at this location here, and we're going to do central difference. So we'll go half step this way. So in terms of this value and this value. So this is equal to t at I plus 1 minus a t at I over delta x minus t at I minus t at I minus 1 over delta x over delta x. So this is equal to t I plus 1 minus 2ti plus ti minus 1 delta x square. So this is the finite difference form for the term del square t del x square, at the location I. And now the transient term. So transient term del t is equal to, we could write t at t plus delta t minus t at t over delta t. So this one I'm going to do the very simple one. So this is only first order accurate. First order accurate, and there are reasons for doing this. This turns out to be the better choice for the type of equation we are deriving. So in terms of the symbol, if J is for time step, like um, like I is for spatial step, so then del t at the location I, at any location I, is equal to t at j plus 1 minus t at j, and we're talking about the location I. So at I, we are talking about j plus 1 minus j, which means j plus 1 is at t plus delta t, meaning delta t time away, and then j stands for t. So that's what they stand for, divided by delta t, of course. So now we have a difference form for the time derivative. So let's try to put the two together. So this time derivative is equal to, so this is equal to alpha times t. This is the part that we already did. So I'm copying this from the previous slide here. So t at I plus 1 minus 2 ti plus ti minus 1 divided by delta x squared. Now the question is, so temperature at node I plus 1, temperature at node I, and so on, they also depend on the time. So these temperatures, we can evaluate this part, the del square t del x square, using a time t or time t plus delta t. Now we want to keep things very simple, and for the simplest case, we're going to use temperatures at time t. So which means these will all have j in there. Now let's try to simplify this. So I can write t at I at j plus 1 is equal to ti j, that's taking the second term here on the other side, ti at j, plus alpha delta t over del x square times t at I plus 1 j minus 2 t I j plus t I minus 1 j. And this is what we wanted to do. So you realize that instead of this differential equation, partial differential equation that is a function of t and x squared and x, we have converted that to an algebraic equation where temperature at I at any time, at a time j plus 1, I can find it from knowing things at the previous time step. So if I know the things at j time step, we can find things at j plus 1. we're going to see that we can use it recursively.